Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. These masterclasses should be used as a study aid and not as a replacement for the 36 regular lectures that are scheduled for Chemistry 209. This lecture, Masterclass 0, provides an overview of Chemistry 209. The material presented here will be discussed in much more detail in subsequent masterclasses. There are a number of additional resources available to students of Chemistry 209. A detailed set of course notes are available on the Course Learn site. There are also weekly tutorial sessions that focus on practical problem solving, as well as numerous online quizzes and practice problem sets. The University of Waterloo Library has a number of textbooks with information pertinent to Chemistry 209. Several of these texts are listed here. In particular, I would recommend Spectra of Atoms and Molecules by Peter Bernath, and Chemical Structure and Reactivity by James Keeler and Peter Wuthers. Spectroscopy may be broadly defined as the study of how light and matter interact. So an important question that we should ask ourselves is, what do we see, since the observation and interpretation of light signals is the essence of spectroscopy. If we take fireworks as an example, we quite obviously see light, which we can characterize in terms of its intensity and color. We also see that our light signals change in position and intensity as a function of time. Observations like these can provide a great deal of information about the chemical and physical properties of matter. The goal of Chemistry 209 is to teach you how spectroscopy may be used to better understand the world around us. For example, why is it useful for us to see in color? Shown here is a junglescape as we would see it in grayscale. Can you see the predator in this picture? The location of the panther is much more obvious when we view the scene in color. Different materials have different colors, and these differences are fundamentally related to chemical composition. Sometimes two different materials will look like they have the same color to us, but that is just because the human eye does not have a fine enough color scale to differentiate between them. Having said this, the human eye is actually a superb spectroscopic detector, and it has served our species well for a very long time. Generally speaking, though, the days of doing spectroscopy by eye are long gone. Modern spectroscopic techniques are not only used to determine chemical composition. Using spectroscopic methods, we can cool matter to microkelvin temperatures, we can determine molecular structures, and we can observe the dynamic behavior of atoms and molecules in real time as they vibrate, move on surfaces, or react. Atomic movements in molecules occur on the timescale of femtoseconds to picoseconds. Thus, this spectroscopic subdiscipline is known as femtochemistry. Most spectroscopy, however, isn't performed in the time domain, but instead in the frequency domain. Still, the most common use of spectroscopy for chemistry students is in determining chemical composition. Usually you will employ infrared or IR spectroscopy and/or nuclear magnetic resonance spectroscopy to confirm that you have prepared the correct product or to deduce the identity of an unknown chemical sample. Spectroscopy is, however, useful beyond the laboratory. For example, have you ever wondered how it is that we know the velocities and compositions of distant stars, nebulae, or galaxies? Earth is constantly bombarded by electromagnetic waves ranging from low-energy radio and microwaves through to high-energy X-rays and gamma rays. By analyzing the light signals in the radio frequency range, for example, we have been able to identify more than 130 molecules that exist in the regions between star systems. Interestingly, though, we also find that numerous frequencies of light are absorbed as they pass through interstellar space, and despite the fact that these diffuse interstellar bands were first observed in 1921, to this day we have not conclusively assigned one single line to a known chemical absorption. The identities of the atoms or molecules responsible for the diffuse interstellar bands is considered one of the biggest open questions in science. To determine the chemical composition of distant astronomical bodies, we must first measure the spectra of chemicals under controlled laboratory conditions, then examine the spectrum of our star or nebula of interest to see if those chemicals are present. Usually this Earth-based research also involves a healthy dose of spectroscopic theory, since this allows us to test and refine existing physical models and make predictions about unobserved phenomena. A nice example of this interplay between experiment and theory occurred between scientists at the University of Waterloo and the University College London when they discovered that water exists on the Sun. Interestingly, the high-temperature water spectra that they observed in the solar atmosphere are also observed when monitoring the emissions from jet engines. Thus, this research had an unforeseen spin-off application in tracking air traffic. Useful applications of spectroscopic methods and instruments are common, and a number of these applications will be discussed in Chemistry 209. For example, the phenomenon of blackbody radiation is the scientific basis for devices such as heat-sensing cameras and night vision goggles. It turns out that any material, regardless of composition, that has a temperature of 300 Kelvin will emit light in the infrared region of the electromagnetic spectrum. Likewise, blackbody radiation for materials at 3000 Kelvin occurs in the red region of the electromagnetic spectrum. The explanation behind this phenomenon is one of the most important concepts in science, since it was at the heart of the quantum mechanics revolution in the early 1900s. Thus, most of our modern technology arises due to Max Planck's theoretical spectroscopic research on blackbody radiation. Interactions between light and matter occur throughout the electromagnetic spectrum. Absorption or emission of light in the microwave region causes changes in the rotational states of molecules. Vibrational excitations typically occur when light in the infrared region is absorbed, and absorption of visible or ultraviolet light can cause electronic excitations. The highest energy process that we will study is ionization, which generally requires absorption of short wavelength ultraviolet light. The lowest energy process that we will investigate will be transitions between nuclear spin states. These are typically induced with radio waves. We will begin our study of spectroscopy by discussing basic spectroscopic theory. Here you will be introduced to basic quantum theory, since this is the principle that underpins modern spectroscopy. We will build an understanding of how very small particles can exhibit wave-like properties, and see how this concept evolves into the notion of atomic and molecular orbitals and quantum states in matter. When we have developed a rudimentary understanding of quantization, we will see that we can explain the emission and absorption spectra of atoms and molecules from fundamental physical principles. This understanding allows us to move beyond using spectroscopy for simple sample identification, enabling the development of molecular orbital theory and band theory, which forms the basis of modern chemistry. We will see that measuring transitions between rotational energy levels provides information on molecular moments of inertia, which enables us to precisely determine molecular structure. A well-known application of rotational spectroscopy is the microwave oven, which takes advantage of transitions in water molecules to heat hot pockets and leftover spaghetti. Vibrational or infrared spectroscopy is ubiquitous in modern chemistry laboratories. It facilitates chemical identification and provides a means of measuring bond strengths. When we discuss vibrational spectroscopy, we will spend some time talking about symmetry as it applies to molecular systems. You will see that symmetry plays an important role in how we classify molecules, and it has important bearing on which spectroscopic transitions occur and which do not. You will see that Raman spectroscopy may be thought of as complementary to infrared spectroscopy. Rather than measuring absorption or emission of light, Raman spectroscopy instead measures the light that is scattered by molecules. Among other things, Raman spectroscopy is used to monitor natural gas emissions and to non-invasively scan biological membranes, and in our discussions of Raman spectroscopy you will learn why the sky is blue and why sunsets are red. Electronic spectroscopy is something you already have experience with. Processes that absorb or emit visible light typically involve electronic transitions. The blue-green color of candle flames, colored emission of neon and sodium vapor lights, and the greens, blues, and purples of the northern lights are all due to electronic transitions in atoms and molecules. When an electron in an atom or molecule is given enough energy, the electron is ejected and the atom or molecule is said to be ionized. You might consider the process of ionization to be the limit of electronic excitation. Using light to accomplish this is known as photoionization. Owing to the quantized nature of energy levels, ejected photoelectrons may only have very specific kinetic energies. These kinetic energies are characteristic for each different atom or molecule. The Mars rover takes advantage of this phenomenon to chemically map the surface of Mars with an instrument that was designed and built at the University of Guelph. The final topic that we'll discuss in Chemistry 209 is nuclear magnetic resonance, or NMR spectroscopy. NMR is probably the most widely used spectroscopic technique for determining molecular structure and chemical composition. One of the most common uses of NMR techniques is in magnetic resonance imaging, and you will learn how functional MRI is used in psychology research to map the brain. As a final note, you should be aware that spectroscopists treat energies, frequencies, and wave numbers equivalently and often jump back and forth between several different units. An important part of Chemistry 209 will be getting used to the language that we use and getting to terms with units. Remember that numbers without units are meaningless. You will find lots of practice problems dealing with this online and in your first tutorial. See you next time.